Welcome to a read along with Dr. Pell in the book Discrete Perspectives in Mathematics. This is section 4.4 on elliptic curves, and we're just starting it out. Okay, so first of all, elliptic curve is a name of a group. Okay, and we're going to talk in this section about first about some motivation for the name of these groups as elliptic curves, in particular the word elliptic. Okay, well, first let's think about cosine and sine. These are functions that parameterize the x and y coordinates on a circle. Say it is in radian measure. Radian measure is the same as arc length. So these are functions where the intake is arc length on a circle and the output is certain coordinate values. Okay. Now, what if we were to look at another shape, not just a circle, but like an ellipse, and think about a function that goes from arc length to maybe certain coordinate positions in relation to an ellipse. So from a circle, those are what we'd call trigonometric functions. Now from an ellipse, different coordinates and ratios would be called Jacobi elliptic functions. And here's just a couple of those. So a few of those: Sn, Cn, and Dn. And anyways, they're just like a circle can be parameterized by cosine and sine, and other curves actually are parameterized by cosine and sine. You can call them kind of like, if you'd like to, like circular functions if you want to, because they are parameterized by cosine and sine, the cosine and sine function. Well, there's other curves that are actually parameterized by these elliptic functions, you could say, instead of the circular functions. There's ones that are parameterized by those. So not just a circle is parameterized, but you could have like any old curve, right? That's parameterized by cosine and sine. Here, there are particular curves or polynomials type graphs in y and x where that are also parameterized but they're not parameterized by circular functions, by elliptical functions. In particular, here's a parameterization: x is equal to Sn of ellipse arc length, y is equal to Cn times Dn, where these are different elliptical functions. Now, their output, you could look that up or Google it or whatever if you're interested in specifically on what these output in relation to coordinates or ratios and so forth on ellipse and what kind of ellipse and so forth. But there are certain curves like this, like y squared is equal to some degree for polynomial in x, which are actually parameterized nicely by elliptic functions. Okay, but we're going to be taking a look at other functions which have similar origins. So they're parameterized by functions, not necessarily the same ones, Cn, Dn, and Sn, but they're parameterized by functions that are similar to these, or they come from similar places with arc length, but not, and so we're going to again call them elliptic. We're going to call this elliptic curve since it can be parameterized by things that are similar to these other guys and have similar properties to these elliptic functions. And so again, we kind of broaden our category and call those ones elliptic. And then we get that we could call this an elliptic curve, not a degree 4 necessarily, but this is a degree 3. Anyhow, so this is an example of an elliptic curve. Yet, for some a and b value, but we're going to reserve the name elliptic curve specifically for types of curves which satisfy a certain criterion. This one we wouldn't call at least an elliptic curve in the sense that we want to, and that's because we're going to define an addition between points, like we're going to be adding 2 points, and that addition depends on the fact that at each point there is a unique tangent line. Well, right here, there's a problem. There's like 2 tangent lines you can pick from. And so we won't consider this as, at least in our case, as an elliptic curve, just because we want the elliptic curve to specify the type of group that we're, the type of setup that we want for the group operation to hold. Okay, so, okay, and this is the graph of this, okay, and we can use implicit differentiation. So we take a derivative of both sides with respect to x. It looks something like this, the chain rule, 2y times dy dx right here. We get something like that, and we can solve for dy dx. And you'll notice that at the point 1, 0, which is the point in question right there, notice we have something happening. We have like a 0 times dy dx is equal to 0. So if we solve for dy dx, we'd have like a 0 over 0. And if we want to avoid like problems like this, it suffices just to avoid 0 over 0 type situations in solving for dy dx. So, for instance, let's suppose that we take this curve, y squared is equal to x cubed plus 3x plus 2. Here's the graph, and implicit differentiation yields this. 3x squared plus 3 is always positive. Oh, so that means it's never 3x squared plus 3 is never 0. So we'll never get a 0 over 0 situation as we solve for this, which is nice. So we can definitely call this an elliptic curve. It's smooth enough for this distinction. It doesn't have any funny crossings or other tangent problems. Okay, so that's kind of the setup and the introduction for what we're going to be looking at. And that concludes this little read along. And the next one, we'll actually start thinking about what this addition between points actually is. Thanks for watching.